My name is Auwal Bala Abubakar. Today I'm going to give a talk on our new work, which was recently published, titled New Hybrid Three-Term Spectral-Conjugate Gradient Method for Finding Solutions of Nonlinear Monotone Operator Equations with Applications. Being part of the postdoctoral seminar series of the Center of Excellence in Theoretical and Computational Science, Faculty of Science, King Monguti University of Technology, Tomburi. So the outline of my talk is as follows. I have the introduction, motivation, the proposed method, convergence result, numerical experiments, and then finally the application. So our aim in this work is actually to find an approximate solution to this problem one, trying to find a y in D such that bar theta of y is equal to 0, where the function bar theta is from Rn to Rn, is monotone and ellipse is continuous, and the set D is the subset of Rn, which is assumed to be non-empty, closed, and convex. This problem one has so many applications in various fields, be it power flow equation, chemical equilibrium systems, economic equilibrium problems, and several others, image recovery, signal processing, and so many of them. There are several methods, such as Newton method, for solving this kind of problem. However, due to some of the shortcomings of the Newton and quasi-Newton methods, alternative methods were introduced. Now, among the trending methods for finding solutions to one are the CG method and the spectral gradient methods. In addition, among the advantages of this conjugate and spectral gradient methods is that they require only the function value of the operator defined in one. Again, an important aspect of these methods is the definition of the parameter involved. So what is much more important when dealing with CG and SP algorithms is the parameter involved, which is either the CG parameter as in the case of the CG methods, or the spectral parameter as in the case of the spectral method. So these two things, or these two parameters, are more important, or the focus of most of the research in this area. So people are trying to improve on these parameters so as to get algorithms that are more efficient and robust compared to existing algorithms. Now we have some notable CG parameters, which are existing methods, CG parameters. We have the Pollack-Ribery Pollack, which is the PRP. We have the DY-1. We have the HS, which is the Hastings-Stifel, and we have the Fletcher-Reeves. And these parameters are defined as follows in 2 and 3. These are not the only parameters we have. We decided to bring them here because these 4 parameters are the parameters we are interested in this work. Where bar theta k stands for bar theta of yk. So it means the function you evaluate yk, bar theta of yk. Zk minus 1 is the difference between the images of the previous yk and the current yk. Now the CG method follows this process. So given an initial point x0, to get the next point you use equation 4 by taking xk plus alpha k dk, where alpha k is the step size and dk is the called the CG direction, which is given by this. When k is 0, you compute negative of bar theta at x0, and when k is greater than 0, you compute minus bar theta of xk plus the CG parameter multiplied by dk minus 1. So in this case, x0 should be y0 in this case, so that to follow the because we are using y as the variable. So this is a typo. Now the motivation. Now we are motivated by two sets of methods or two classes. In this slide, I decided to use these 5 methods as motivation for the first part of the motivation. So all these methods mentioned here are all algorithms, or 4 algorithms here. They are all proposed. For example, Yahukosh proposed a 3-term conjugate gradient method to solve one. What he did is he modified the PRP algorithm, and he added an additional term to the PRP just to achieve the descent search direction, so that the search direction should be descent. So he added another term because the PRP for solving one, if you look at it carefully, it is not actually descent. So he added a term to it such that the search direction is going to be descent. So this is one of the motivations, because in our work also we added a term such that we would like the direction to be descent to satisfy a certain inequality we are going to see later. Similarly, Liu and Feng did descent into the Dai-Yuan algorithm, introduced a spectral parameter to achieve the descent direction. Similarly, Yan et al. Proposed a modified hastiness HS algorithm. He added a new term also such that to achieve the descent direction. Also, Abubakar et al. Proposed a modified Fletcher-Ridge algorithm by adding another term to the Fletcher-Ridge algorithm such that the search direction is descent and bounded. So these are some of the motivation in one sense. So what we are going to propose, we are going to see that we are going to add additional term to the direction just to achieve that particular property we are interested in. And why we are interested in that property is because that property is crucial in showing the convergence of the method. Now the second set of papers that we are motivated with are the hybrid methods. So all the papers I mentioned here are hybrid. For example, Kylo and Koropetse proposed a new hybrid progression method. The algorithm can be seen as a combination of the HS and DY. So what they did is there is a HS algorithm, there is a DY algorithm. So they try to combine the two algorithms to see if they are going to have an improved algorithm, because both the HS and the DY has their own advantage. So combining the two, perhaps a more advantage will be obtained. So that's what they did. Sabu et al. Also proposed a hybrid conjugate gradient method, combining the FR and the PRP method. Ibrahim et al. Also proposed a hybrid algorithm, combining the leaf story and the FR algorithm. Likewise, a spectral projection method that selects its search direction as a convex combination of two different spectral parameters was proposed by Abubakar et al. So if you look at all these references, you will see that all these hybrid methods consider combining two existing CG algorithms, and most of them consider convex combination, that is combining them in a convex combination manner. So after going through all the first set of the motivation and the second set of motivation, so we decided to see, okay, how can we do something different? Since most of the time people are just considering, researchers are considering combining two algorithms, two CG algorithms, and most of the cases they use convex combination. So we thought about it and said, okay, can we do something different from what others are doing? So the first thing that came to my mind is that if possible, we can have a combination of more than two algorithms. Because all what the researchers have been doing is combine two, not more than two. So I thought about it. I said, okay, let me see if I can combine more than two algorithms, and in a different way, not like convex combination. So this is actually the motivation. So inspired by the above hybrid method, we proposed a new spectral conjugate gradient method. The new hybrid method, to the best of our knowledge, is the first of its kind. And an important thing to this algorithm is that it has special cases. The PRP is going to be a special case. The DY type method given in 11 is going to be a special case. The HS type method given in 18 is also a special case. And the FR method is also going to be a special case of this new algorithm. The side direction is also descent and bounded, independent of the line search. Now, the side direction we are going to propose, we are going to see later, is comprised of two parameters. The first one is the hybrid CG parameter denoted by beta k and h. So NH stands for new hybrid. And the parameter denoted by lambda k and h, which is the spectral parameter. Derived. So we derived this spectral parameter to ensure that the side direction satisfies the following inequality. So this part, the last part, obtaining that parameter lambda k and h is actually motivated by the first set of papers I mentioned. And the beta k and h, which is the CG parameter, which is a combination of 4 different CG parameters, is actually motivated by the second class of papers I mentioned, where they combine 2 algorithms using convex combination. So this is what we define. So the parameter beta is a combination of 4 distinct well-known CG parameters, and it is defined as follows, given by 6. So what we did is we observed that among these 4 parameters we are considering the PRP, HS, DY, and we observed that some of them have the same numerator and some of them have the same denominator. So that is what gave us a soft landing on how to actually define the beta k and h in 6, where zk is given by 7, beta k minus 1 is given by 7 also as well, and lk minus 1 is given by 8. Now, if you observe, if you take C1 equal to C3 equals to 1, and you take C2 equals to C4 equals to 0, this beta k and h will now go back to beta k PRP. So beta k PRP is a special case. So if we take C1 to be equals to C3 equals to 0, and C2 equals to C4 equals to 1, then beta k and h will now become equals to beta k PDY, where beta k PDY is a modified DI1 CG parameter proposed by Liu and Feng, which is among the papers I mentioned in the motivation. The third case is if you take C1 equals to C4 equals to 1, and C2 equals to C3 equals to 0, then beta k and h will now become similar to beta k MHS, which is a modified Hessenus-Stifel CG parameter proposed in 18. And then the last case is if you take C2 equals to C3 equals to 1, and C1 equals to C4 equals to 0, then beta k and h will just be equal to the beta k FR, which is the Fletcher use. So next we will define the new hybrid 3-term side direction as follows. So we define D naught to be equals to minus by theta naught, dk equals to dk and h, which is the new hybrid direction, which is given by 9. So where beta k and h is given by 6, we have mentioned it earlier, and lambda k and h is derived such that the inequality 5, which that inequality I mentioned, which is very important, is satisfied. And after the derivation, we choose this spectral parameter to be equal to the CG parameter multiplied by another parameter, which is theta, but theta k transpose dk minus 1, all over norm of theta k squared, provided the norm of theta k is not 0. This is very important because if norm of theta k is 0, so it means we are already at the solution. So we assume the solution is not obtained in this case. If this is obtained, we are not going to reach this step. So this lambda k and h is actually derived such that inequality 5 will be satisfied with m equal to 1. So in our case, m in that inequality 5 is equal to 1. Now it is worth noting that one of the advantages of the new hybrid algorithm is that it possesses the features of all 4 classical algorithms, namely the PRP, DY, HS, and FR. Now, to prove the convergence, we assume the following. We let sol of D per theta denote the solution of problem 1, and assume the following conditions or assumptions hold. The first one is the constraint set is non-empty, closed, and convex. Assumption 2 is that the operator where theta is monotone and LH is continuous on Rn, that is, inequality 11 and 12 are satisfied. Next, we give the algorithm. So what we do is we choose an initial guess y naught from D in Rn. C1, C2, C3, C4, and mu greater than 0. Theta is between 0 and 2, strictly. Rho is strictly between 0 and 1. T is greater than 0, tol is greater than 0, and K is equal to 0. So in step 1, we check the tolerance from the initial guess we choose. If the tolerance is satisfied, we terminate the algorithm, else we move to step 2. In step 2, we compute the direction using 9. We compute a trial point using 13. And where alpha k is defined as mu rho to the power of I, where I is the least non-negative integer satisfying 14, which is the line search. And then we check this condition on gamma k. If the condition is satisfied, we stop. Else, we compute the next point using the projection strategy, which is already mentioned in the previous talk. And in many talks, we have also mentioned about it. Where this psi k is given by 16. So in step 5, we increase k by 1 and repeat the process until the stopping condition is satisfied. So the convergence result next. So the search direction defined by 9 satisfy inequality 5 with m equal to 1. So already this, from the derivation of the lambda k nh, you derive it in such a way that this inequality 5 is actually satisfied with m equal to 1. So from the derivation, we already have this lemma to be 2. Then lemma 2, in lemma 2, we have two things. The first one is we show that the algorithm is well defined, meaning that the step size, the step length is actually well defined. And the second one is we show that the step size is actually bounded away from 0. These two, Roman 1 and 2, are also crucial in actually showing the theorem or proving the theorem convergence. Number 3 is if assumption 1 and 2 are satisfied, then the sequence gamma k and yk defined by 13 are bounded. Besides, equality holds, equation 18 also holds. Then finally, using these 3 lemmas, we establish the main theorem of the work. Suppose assumption 1 and 2 are satisfied. If yk is a sequence defined by 15, then lim f of this is equal to 0. Furthermore, the sequence yk converges to a solution of problem 1. The full proof of this can be found in the paper, which is already published. So next is the numerical experiment. So after designing your algorithm, proving its convergence, the next task ahead of you is to actually show its efficiency by comparing it with existing algorithms, similar algorithms, to show whether it's actually efficient and worth publishing. So one way is to test the efficiency of an algorithm is compare it in the first time with similar algorithms. And we make use of the dollar and more performance profile, which is defined as follows, which has been mentioned in several talks in this research group. So the metrics we considered are the number of iterations, the number of function evaluation, and the CPU time. So we use these metrics to evaluate the algorithm and existing algorithm to see whether the new proposed algorithm is actually more efficient than the existing algorithm. So to show the strength, we compare the algorithm with 4 algorithms. The first one is the algorithm called the FPBI V1, proposed by Auwal et al., which is given by this. The second one is called PDY, proposed by Liu and Feng, which is defined also as follows. The third one is the algorithm called algorithm 2.1, proposed by Yan et al., with this. And the last one is the algorithm called MRM, proposed by Abubakar et al. So why we choose these 4 algorithms is because the first one is PRP-like, and we know that PRP is one of our special cases. The second one is also a special case, it's directly a special case of our algorithm. So that is why we choose it, which is the PDY. The third one is also similar, very similar to the third case or special case of our algorithm. And the last one being an FR-like method, that is Fletcher-Reeves. So we also consider it because we have special PRP, DY, HS, and FR as special cases. So for the numerical experiment, we consider 9 test problems. We consider 5 dimensions. We consider 5 initial points. And the control parameters, we select the following as our control parameters. So C1, C2, C3, C4, finally we just put them as 1. As for DFPD1, PD1, 2.1, all the parameters are as given in their respective papers. The stopping condition is when the norm of theta k is less or equal to s power minus 15, or the number of iterations exceed 1000 without reaching a solution. So this is the first comparison of Dolan and Moore with respect to number of iterations. So you can see we have 5 algorithms. We have the proposed algorithm, which is called NHSCG, New Hybrid Spectral Conjugate Gradient Method, and the 4 algorithms compared with. So you can see that from this, the new hybrid method performs better. If you look at the y-axis, you will see that it has almost 70% success in terms of number of iterations, meaning it has the less number of iterations in almost 70% of the problems considered compared to the other algorithms. And similarly, with respect to the function evaluation, you can see the new hybrid method is also more efficient or has the less number of function evaluation than the existing algorithms. And finally, with respect to the CPU time, which is the last metric we considered, you can see that the NHSCG also has the least CPU time in almost 80% of the problems considered. Now the next is application of signal recovery. So in this subsection, we aim at evaluating the efficiency of the proposed method for recovering the sparse signal in compressive sensing. The mathematical formulation of signal is generally modeled as this. So because of we have so many talks that deals with this, so if you want to see more about this model, you can refer to reference 8. So the proposed NHSCG method is compared with several other well-known methods, such as the modified Fletcher-Reeves proposed in 2, the projection method for solving convex constrained monotone equation PCG by Liu et al., and the conjugate gradient for solving constrained monotone equation called CGD by Xiao et al. So we compared the new proposed algorithm with 3 other algorithms. We use the mean square error as a metric to compare the new proposed method and existing method. And we also use the CPU time and the number of iterations also. So we implement the experiment choosing the size of the signal to be n to be 2 raised to the power of 12 and k to be 2 raised to the power of 10. And the proposed algorithm is implemented using these parameters. C1 equals to 0.1, C2 equals to 0.2, C3 equals 0.3, C4 equals 0.5, rho is equal to 0.8, T equals to 0.001, and theta equals to 1. And for the other algorithm compared with, we choose the parameters as in their respective papers. So the merit function considered is given by 27, and the regularization parameter lambda is chosen similar to that of Liu and Li, which is given by 0.05 norm of A transpose B, norm infinity. So the initial point is starts at N transpose B, is being used in starting the experiment, and the experiment is terminated when this inequality actually holds. So this is the figure for the signal recovery. The first is actually original signal. The second one is actually the stop signal, the one that is noisy. And the last 4 are the recovery by each algorithm. So in the first one, you can see that the MSE of NHSCG is the list, though they are all 10 raised to the power of -6, but that is the list. and it has all, it recovers the noisy back to the original in 94 iteration and 2.73 seconds, while all others have higher iteration and higher time of recovery than this algorithm. So, and the proposed algorithm, sorry. And then we repeat this algorithm a number of times, and we took the average. So you can see from this table, we repeat the algorithm, the process like 10 times, and we record the time, the iteration, and the MSE at each iteration. At each time, we run the algorithms, and then we took the average. So with respect to the time and the iteration, you can see the average of the new algorithm is the least. However, in terms of the MSE, it is better than MFRM, but not less than those of the PCG and CGD. Though they are all 10 raised to the power -6, but the PCG and CGD has the least average of MSE. So this is one area we have to look and see how we are going to improve on this, because so many people are not interested in actually having the least time or the least number of iteration, rather to have the least error, because that is what tells you the actual how good is the approximation, is the error. Always tell you how good the approximation is. So this is one area we have to see how we can improve. Though it is almost the same because it's all 10 raised to the power -6, but we prefer to see something less than existing algorithms. Here are some of the references we considered, and thank you for your attention. Please, you can make comments, observations, suggestions on how we can improve our work further. Thank you very much for your attention.